Hello, welcome to Lead Programmer. Today, we are going to solve the question binary tree upside down. So essentially, we should uh, convert the binary tree to its upside down form. So by that, we mean the left child becomes the new root, the root becomes the new right child, and the right child becomes the new left child. And this can be inferred by reading the description. Okay, so let's apply this in the given example. So in the given example, we have 1, 2, 3, 4, 5 represented as this. So here we see that the left child becomes the new root. So in this case, we can either go this way, 2 becomes a new root, and the the root becomes the new right child. So this is essentially the right child, and the right child becomes the new left child. So it's something like this, where 2 is the root, the right child is 1, the left child is 3. Again, for this particular node, we go left again. We see 4, so 4 becomes the root. The left child is 5, and the right child is 2. Giving us something like 4, 5, the right child is 2, we have left child 3, right child 1. Same as this over here. Okay, so we kind of observe a pattern. The leftmost child would essentially be the new root of the entire tree, right? So in this case, 4, which is the leftmost child of the entire tree, becomes the new root. And then the entire tree follows. So let's look at another example here. So to find the upside down tree of this, we go left over here, we go left over here. So 4 becomes our new root. So we have 4 over here. The left child becomes 5, the right child becomes 2. So as shown over here. Great. And then we have 2 over here. So the right child of 2 is 3. So the right child of 2 is 3, and the left child is 1, as shown here. And that's it. So whatever 3 was, that remains unchanged, as you can see over here. So this shows that we only care about the left children, and we do not propagate the change to the right child, because a tree can have only one root, and that root would be the leftmost child, and whatever is there in the right hand child remains unchanged. Awesome. So I think that explanation kind of hints towards what a potential solution can look like. Essentially, we say, okay, we keep going all the way to the left, and once we reach the leftmost root, we want to process it. And one case is, okay, this root has no child. If it does not have any child, we can just return whatever this root is. So it's 4, so we just return 4, and then we come back over here to 2. Now 2 has children, and the children are 4 and 5. So we want to process 2. Now how do we process 2? Okay, we take, okay, so let's say the root is represents the node 2. So the new root would be 4, right? So root dot left would be the new root, and the new root's left child, so the new root's left child would essentially be the right of root, as we said here. So root dot left represents the new root, and the left child of the new root would essentially be the previous right child, as we said in this point. So that would essentially make it root dot right. We also want to mention, we also want to change the right child of the new root. So root dot left dot right would essentially be root, because here we inferred that the new right child would be root. Right, and we would also have to clear the original children. So we would also have to clear the children of root, which is 2. So 2 would no longer point to 4 and 2 would no longer point to 5, because the new root is 4 and now it has its children. So we just reset root dot left and root dot right to be null. Awesome. So let's quickly look at the code. Essentially, we went through it. So if a root does not exist, if root is null, then we just return null. If we encounter a node, like I mentioned in this case over here, where it has no children, then we just return root. We can also change this case where we just check if root.left is null, and we can return root. But in the question constraints, it was given that either a node has no children or it has 2 children. Now, as we discussed, we go all the way to the left. So that's why we have a recursive call here, and we keep passing in the left child of root, and that would essentially become the new root. So once, and that's what we return at the end for a function. But we also have to modify the children of the new root, which we can do by root.left.left. As I mentioned, because root.left essentially refers to the new root, and we set the left and right child of it. So the left child becomes root.right and the right child becomes root.left, based on this, based on what was mentioned in the question definition. And we also have to remember to remove the original links, because those links between two nodes don't no longer exist, because we have a new parent or a new root. So we just set them, those links, to null, and yeah, we return new root. So in the worst case, the time complexity and the space complexity is big O of n. Because if we have a linear arrangement of nodes, then we have to visit each and every node. That's what the time complexity becomes O of n. And since we are using recursion, the space complexity is O of n, because we potentially have everything in memory. Because if we keep going left all the way down the tree, then we potentially have everything in the memory or in the stack. Okay, cool. So I hope it helped. If you have any questions, feel free to leave them in the comments. Please subscribe, and I hope you enjoyed it. Thank you.